Hi, my name is Rina Panigrahy, and I'll be talking about how could the mind be storing information. So let's say you meet someone for a chat over coffee. How do we remember something like this? How is this indexed, represented? And more importantly, if you meet the same person later for a similar discussion, how is this retrieved from your memory? Is there some knowledge graph that we build? And this is particularly important for a conversational system. And note that we are not trying to understand exactly how this is done in the brain, but we're just taking a step back and trying to understand this conceptually as an algorithm. Next slide, please. So if we close our eyes, we can actually recall specific scenes and words and topics from our past, which means that we probably store a sketch of events, and the sketch can be used to approximately reconstruct scenes and sounds and events from the past. And another important property of our mind is of our memory is that it fades gradually. We don't forget things suddenly, but we gradually lose memory of the high level details, and then over a long time we might lose everything. Also, it's probably the case that in our mind, logically, we have many different modules. Like we may have a module for recognizing people. We might have a module for analyzing speech, getting the topics, and get speech embedding, and so on and so forth. But at any one point of time, only a small number of modules may be active. Next slide, please. So logically, we can think that our mind is this kind of a modular architecture that feeds into up the chart into more and more complex modules. And next slide. But at any one point of time, only a small subset of these modules fire in a DAG. And when we want to compute a sketch, we essentially want to figure out which modules fired and with what embedding values. And that is essentially tracking the main things that have been found by this forward path computation. Next slide, please. So how would we store a sketch of these small number of modules that are firing? So pretend for a moment that all the modules are just flat hierarchy. They're just flat. They're not in a hierarchy. So let's say that thousands of such modules, and only a few of them are firing. So in a chat over coffee, only the person module might be firing, and the speech module might be firing, and the specific topic module might be firing. So since this is only a small number of outputs are non-zero, we could use a standard subspace embedding idea to sketch the outputs. And what that does is it essentially packs the output of each module in a random subspace. Next slide, please. And this is done by choosing a random matrix for each module and hitting the output of that module with that multiplying it by that matrix, and then adding up over all the modules. And what you get is a final sketch. And since only a small number of outputs are non-zero, just by looking at the final sketch, you can actually tell which modules fired and with what values. So this is essentially a form of sparse coding. And note that the type is encoded by the direction. So you automatically get type information in the final sketch. So for a person sketch, it will be along the person subspace, and for speech, it will be in the speech subspace, and so on and so forth. Next slide, please. So this is essentially, you can do sparse recovery here, which is like dictionary learning. In dictionary learning, you have a large dictionary of atoms, and only a small number of dictionary atoms are added in any one input, and you can tell exactly which atoms were present. Similarly here, as long as the final sketch has sufficient number of bits proportional to the number of non-zero modules, you can tell exactly which modules fired with what values. So this is a simple idea that you can use for when all the modules are in one level and only a few are firing. And you can make this idea recursive by just each output not tracking just the module output, but also the previous module's outputs. And that'll give you a final sketch which encodes the entire DAG. Next slide, please. So this essentially maps every complex input into a sketch space. And the important thing is that it preserves sketch similarity, which means that semantically similar inputs will have semantically similar sketches. And this just because similar inputs will make the same modules fire, almost same modules fire with almost the same outputs. So if I'm meeting someone over coffee for the next time, the same person module will fire with almost the same values. And that's why you can use that to retrieve the older sketches. And you can automatically get type information by looking at which direction the sketch has, in which subspaces the sketch has components. And also things which are, since the sketch is recursive, things which reference each other will also have similar sketches. So the sketch of a meeting with a person will be similar to the sketch of the person itself. So you almost get like an object-oriented view of the sketch, even though it has a dense representation. And this can also be used for finding new concepts. So let's say someone sees a tiger for the first time. Then in terms of the previous module outputs, so let's say it's the image analysis module, which is output from image features. In terms of that sketch output, you will start seeing points in a new region. So all the different tigers might form points in a small cluster. And by identifying a small new cluster, you know that you're seeing a new concept. And so that could be used to train a module for a tiger. Next slide, please. So this automatically gives us a sketch repository, which can form a knowledge graph, because similar events will have similar sketches, and things which reference each other will point to each other. And the modular network could interact with these sketches. So every time you get a new input, you could go to the sketch repository, find related events, and consume that for your next actions. Next slide, please. So as a conceptual study, we could prove theoretically that this method can be used to sketch events in a way so that you can retrieve similar sketches from the past and use that for your current computations. We can prove that this has this gradual erasure property, which means that the memory fades gradually, just because these matrices are random. So even if you lose half the bits, you still have a lot of information to get the top level data. But also for the lower level details, you may not remember everything, but you remember some summary of it. So it can be used to get things like, you may not remember all the people in a meeting, but you might remember roughly how many people were there, or if most of them were wearing black shirts, you can tell that you can say that. Next slide, please. So we used this to build a generic neural memory architecture that you can attach to any neural deep network, so that you can consult the memory as inputs are flowing up. Next slide, please. So all we do is we use a locality sensitive hash table to store sketches from the past, so that similar sketches go to the same bucket. And at every layer, whatever output you get, you use that to consult the table and read that and feed it to the next layer. On BERT. Next slide, please. So we tried this on BERT, and we see that we can double the capacity of BERT, which is attaching a small amount of memory and adding only 1% compute. Next slide, please. And on ImageNet, we saw that this is very good for long tail classes. And this makes sense because for the long tail classes, you can remember them in one bucket in the memory. And it's very hard to do that in the ImageNet classifier. So we saw one proposal for how the mind could be storing information based on sketching. And we saw an implementation of neural memory using locality sensitive hashing. Here are the references. Thanks for watching.